It is my honor, and I am very happy to accept the invitation of Professor Bozic to give this plenary lecture. And I agree with Francesco concerning the steps after the acceptance of the invitation. It is unfair to follow Francesco because his very interesting lecture will make my lecture something boring. But I think that at the end of the presentation, we will have more questions than answers, and perhaps this is interesting. So the topic of my presentation is related to the very core question of fracture mechanics. We want to predict, and if it is possible, to prevent catastrophic events. And the main question is whether we can do it. In this lecture, we'll discuss two alternative approaches for elaborating the data that we obtain from two sensing techniques, the acoustic emissions and the pressure-stimulated currents. The structure of the presentation is shown here. We have two pillars, one devoted to the concept of natural time, and one devoted to the concepts of non-extensive statistical mechanics. Then we'll discuss a few applications to see whether it is possible to have some quantitative indices about upcoming disaster events. So the motive is clear. We want to provide answer to the questions whether and how can we predict catastrophic events. Mr. President, after 30 minutes, please give me a sign so that we have some time for questions and perhaps discussions. Now, to be honest, in field applications, we are very far from the end target. We cannot prevent, for example, earthquakes for the moment being. We try, but okay. Let us hope that for the future it will be possible. In laboratory level, due to the fact that we can eliminate noises, which is not the case for practical applications, we have more encouraging results. We have approaches that, based on data from structural health monitoring, provide interesting pre-failure indicators. Based on data gathered by the techniques used for structural health monitoring, if we could define SHM, we could say that it is a procedure to collect and elaborate data from onboard sensors to quantify the damage level of a structure, where damage can be defined as any kind of changes of the material properties, the geometry, the boundary conditions that affect adversely the performance of the system. So if we follow the principles of SHM, perhaps we can optimize decisions about maintenance and repair, and perhaps we can facilitate prediction of catastrophic events. We'll discuss about two techniques used to gather this data. The first one is familiar to all of us. It is the passive monitoring technique called acoustic emissions technique, which is a result of the events that are due to sudden redistribution of the stress field within a loaded structure, which creates an elastic wave that is captured by some sensors. The fact that the waves travel within the structure is the main advantage of the technique because it permits collecting data from positions that are not easily accessible. The main issue while dealing with acoustic emission techniques is the decoding, the proper decoding of the information. It is a very difficult task because it is somehow subjective. While decoding the data from acoustic emissions, we need to parameterize some data, which means that we have to define numerical values for some parameters and also to set some limits to minimize the influence of parasitic noises. This is very difficult, and as I mentioned, subjective. That is why many researchers are looking for additional characteristics that do not depend directly on single hit parameters. In our study, we'll adopt a recently introduced approach, which is based on some objective parameter, the interevent time intervals. Using the time duration between two successive acoustic events or acoustic hits, they're not identical, we could define a function f which reflects the average frequency of generation of hits. Now, if we pair the values of this function with the average time that these acoustic hits or events are generated, we can plot this function and draw some very interesting conclusions about the damage mechanisms activated. So if we have a time series, we can isolate a number of events, calculate the function for the first group, and then removing the first one and adding the next one, we can obtain the new value. And so we can plot a time function, which provide very interesting data about the damage mechanism, as I mentioned. Now, acoustic emissions do not need any further data. It is familiar to all of us. But very recently, an additional technique is developed based on the fact that we observed experimentally that during loading, both piezoelectric and non-piezoelectric materials, we have emissions, electromagnetic emissions. Among these emissions, special attention is paid to the very weak electric currents developed, which were observed already since 1975 by Whitworth. The main issue related to these currents is that they depend on the stress level. They start being generated at the transient interval between the linear and non-linear response of the material. As yet, there is not a definite model describing and quantifying these pressure-stimulated currents. There is a variety of models. To my opinion, the most well-based one is the motion of charge dislocations, the MCD model, which depends on the charge dislocations and the motion of charge dislocations. There is a mathematical basis. These slides are wide because I will not insist on mathematical details. The presentations will be available. The slides were available after my speech, and so you can draw some information about the reference that you can use to find details about the mathematical background. What is very important is that following the temporal evolution of these pressure-stimulated currents, we can detect critical stages. You can see here a very simple test, uniaxial compression of marble, Dionysus marble. And we have plotted here the load, the orange line, and the electric current. You can see that while the load is very low, or it is in the linear region, the pressure stimulated current is almost zero. As we are approaching the non-linear response of the material, the threshold between linearity and non-linearity, which for most brick materials is the threshold between reversible and non-reversible deformations, the electric current starts increasing smoothly and then very rapidly. This onset of generation of electric current, according to the MCD model, is related to the entrance into the stage of formation of dense networks of microcracks. Then, as the load approaches its maximum value, you can see that the electric current starts decreasing a little before the load starts decreasing, which provides us with a tool that something will happen very soon. This very soon is a problem. We'll see it later. So there is a second critical point, the onset of rapid decrease, which, according to the MCD model, designates the onset of coalescence of the networks of microcracks in the direction of formation fatal macrocracks, which interrupt the electrical paths available. That is why the electric currents are decreasing. So, having described shortly the two sensing techniques that we will use, there is a variety of techniques, of course, we can describe shortly the two methods for the analysis, these two alternative methods for the analysis of these data. The first one is the analysis in the natural time domain. What do we mean by the term natural time? Suppose that you have a series of acoustic events, or of events in general, a time series. Then, according to the natural time analysis, we assign to each event a pure number, which is the order of appearance of the event over the total number of events. We define the order of appearance, starting from 0 to 1. Then we pair this value with the energy emission during the specific event. And so we have a function that describes the order of appearance of any event and its energy constant. This is due to the point of view that we are interested about the sequence of the events, either they are events or earthquakes, and not to the external reasons that produce these events. So natural time is in contrast with the conventional time, which is in fact a one-dimensional continuum in real numbers. We'll come back to this point. Natural time was introduced in the field of seismology about 20 years ago, after a long series of observations of earthquakes. And you can find many details about this concept in a milestone book published by Springer. Nowadays, natural time analysis is applied in a very broad field of disciplines, starting from mechanics to medicine. There are applications to the prediction of heart attacks, physics, of course, engineering, structural components, and so on. There is a very big list of studies dealing with applications of natural time to very broad variety of disciplines. Now, having introduced the natural time, we proceed to the introduction of the normalized energy emitted during each event by this function here, by this definition. And then, since these quantities are positive and summing up to unity, we can treat them as probabilities. In the frame of probability theory, we can extract information about the evolution of any time series by the characteristic function, familiar to people working with probability theory. Or even better, by the normalized spectrum, if we pay attention to natural frequencies approaching 0. If we expand the natural frequencies and the characteristic equation in terms of Taylor expansion, we define the variance K1 in natural time. This is a very critical quantity, as it will be seen soon. In addition, we introduce the entropy in natural time concept by this equation here, which is a dynamic entropy. It does not coincide with statistical entropies like that of Shannon. It exhibits positivity, concavity, and experimental stability. And in case we have a complex system that is stable and the events are independent, or we have identically distributed variables, then the entropy tends to a critical value, which corresponds to the so-called uniform distribution. Now, the third quantity that we have to introduce is the entropy upon time reversible. It sounds strange, perhaps, we cannot reverse the time arrow, but since the entropy describes quantities that do not obey to time reversal, we should check whether applying a reversal operator, we obtain a different value for the entropy. And this is the case. The value obtained, S underscore, does not coincide with the entropy under the normal time arrow. And so we have a verification that our approach satisfies the causality rule. So K1 is stable, does not obey and does not change upon time reversal. I have some very interesting slides about time reversal, which seems to be scientific fiction, but for people working in thermodynamics and physics of complex systems, it's very important to discuss how a system would behave if we could inverse the time arrow. You can find details in some references here. What is very interesting is that when a system, a complex system, a dynamical complex system, is ready to enter into a new dynamical stage, then we have fulfillment, simultaneous fulfillment of three restrictions. K1, the variance, must be equal to a specific value, 0.07, and both the entropy and the entropy upon reversal of time should be smaller than the uniform distribution than the value of entropy at the uniform distribution. I can show you a very simple example with a very simple experiment, a 3-point bending of plain concrete. We'll discuss also fiber reinforced concrete later, to see the response of a system if it is discussed in terms of natural time. So you can see here the response, the mechanical response of the system, the sensors used to gather the data, electrical and acoustical sensors. And you can see here the response in terms of load and time. This is the acoustic activity. As it is expected, it is very intense at the very last loading step. And it is quite possible that we lose interesting information if we study the system in this conventional time. And you can see here the electric activity. Again, the electric current is almost zero or very slowly increasing. And as we proceed to the transition between reversible and irreversible phenomena, it starts increasing and then decreases suddenly. Again, everything happens a few seconds before fracture. If we plot the same data in terms of the natural time domain, this figure here, you can see that we have a more uniform representation of the data, and we can extract additional information. You can see, for example, that this area here, which in the conventional time has a duration of 3 or 4 seconds, I think, if we plot the data in natural time terms, this area is transformed to this area, and you have a very clear observation of the evolution of the load and other quantities during the very last seconds of these phenomena. Now, we can plot the 3 critical quantities, the variance and the 2 entropies. You can see that we have 2 areas where all 3 conditions are satisfied, which means that there are 2 critical conditions. The system enters to a critical condition at time instant, natural time instant 0.19, and also at 0.18. All this area, remember, corresponds to the last 10 seconds, roughly, of the experiment. So we have 3 critical conditions. Now let us see what happens with electric emissions during these 2 critical conditions. You can see that in the first critical condition area, the electric current, the red line, starts increasing abruptly. So according to what we mentioned, it is the entrance to the stage of intense generation of microcracking. Then, as we approach the second criticality area, the electric current starts decreasing, which means that we entered the region, the critical region of coalescence of microcracks to the formation of macrocracks, which leads finally to the fatal fracture. So indeed, the data provided by the natural time concept and the pressure stimulated currents are in very good agreement with each other, and each one can help us in explaining the response of the next. What is the time, Mr. President?
Well, bad news.
Bad news? No. Now, the second tool to analyze such data is the non-extensive statistical mechanics. Starting from Boltzmann, who opposed the statement of Clausius that we cannot quantify entropy. As we all know, Boltzmann introduced a different description of entropy that could be quantified based on the total number of microscopic configurations and the possibility, the probability for each configuration to appear. We have one of the pillars of physics, the traditional Boltzmann-Gibbs statistical entropy. Now, quite a few very important developments in physics were based on Boltzmann-Gibbs statistic entropy. However, this entropy is based on some simplifications. The most important is that we have systems that the micro events are nearly independent. This is the case for many practical systems, but we know also that there are systems that do not obey this approach, systems that are not ergodic. These systems cannot be described by this entropy, and so additional entropies are introduced, which are non-additive. contrary to Boltzmann entropy. The concept of ergodicity can be understood if we see the two figures. Suppose that you have a particle of a gas. If all states are equally probable, the first figure, then all possible positions within the block can be occupied. If you have a non-ergodic system, then the system is composed of two different subsystems. So the definition of this entropy by Kourkoulis, which is the most widely used one, is this here. For equal probabilities, you can see that the main difference is that while Boltzmanns have a definition based on the logarithm, the entropy by Kourkoulis is dependent on a Q logarithmic function defined as you can see here. Only if this index Q is equal to 1, the two entropies are identical. And this index Q is very important because it is a measure of the non-extensivity of the system. And then we can describe systems that consist of non-independent subsystems with long-range interactions and memory effects, which will be proven very important in the analysis of non-homogeneous structures. It is obvious, based on the definition, that Kourkoulis entropy is non-additive. I will skip some details. Mathematical details are available to you, and we can discuss on them. And let us see how could we apply this concept to analyze data from structural health monitoring. The most easy way to do this is to use again the interevent times as the parameter of the non-statistical entropy, the interevent time between two successive events. So if we analyze and plot the data, we can define the probability function, and then it is proven that it obeys a specific law based on Lagrange multipliers. So if we plot the cumulative distribution function and fit the data by this equation here, we obtain the values of the entropic index Q. The entropic index Q, as I mentioned, defines the existence of subsystems within a loaded system. And skipping details, it is very interesting to see what is the temporal evolution of Q in the example we discussed with natural time analysis, the simple three-point bending test. If we plot this index Q, you can see here that at early loading steps, it is increasing, which means that we are moving away from Boltzmann-Gibbs uniform system towards a system that consists of many subsystems. What are the subsystems? The networks of microcracks, which interact to each other, but are nearly independent. So you can see here that Q increases following the increase of the load, and then it reaches a peak before the maximization of the load, which is very important in case we are looking for pre-failure indicators. If Q reaches this peak, then according to the theory, it means that we have generation of so many independent microcrack networks that they start interacting in the direction of forming macrocracks, which are fatal. And then Q starts decreasing towards the familiar value 1, and the system obeys again to the Boltzmann-Gibbs statistical mechanics. This is not only the case for this specific test. You can see here a three-point bending test with concrete. In terms of time and load, you can see that Q increases starting from 1, Boltzmann-Gibbs statistics, reaches a peak. The value of the peak is not constant, depends on the loading scheme and the material, and that it starts decreasing. So it is safe to consider that this onset of decrease of Q is a critical point that warns about an upcoming entrance of the system to a new stage, a critical stage that will lead to catastrophic fracture. So we compared our results with additional quantities, the F function, the energy of the acoustic events, the b-value, the familiar b-value, and you can check what happens at the critical area around 10 seconds before. This is inverse time arrow. We plot the data according to the time to fracture. And you can see that all three quantities indicate that something will happen at about 10 seconds before fracture. The energy starts increasing abruptly. The frequency of generation of peaks increases abruptly. B-value starts decreasing towards the critical value of 1. So we have a coincidence of the predictions of various tools with this of natural time and the non-extensive statistical mechanics. I will skip many applications, and I will go directly to some slides with structural tests. We have a variety of experimental protocols indicating that indeed natural time provides pre-failure indicators in many different geometries and many different loading schemes. And let us see what is the case if we have structural tests, means specimens, which from the very beginning are composed by different subsystems. The first case I will discuss is epistyles of the Parthenon table under shear. You can see here the sketch of the loading scheme, the experimental protocol, and the data, which means the time and the amplitude of the acoustic emissions, the F function, and the pressure stimulated current. If we plot these data in terms of non-extensive statistical mechanics, we will see that these three regions, which were identified by means of digital image correlation, optical fibers, strain gauge, and so on, provide us with this very interesting picture. As the load increases, almost monotonically, you can see that we start now from a high value for Q, because from the very beginning, we have a system with subsystems, the two blocks, which are interconnected by means of the metallic connector and concrete. So the Q value starts decreasing, and at the onset of intense cracking, it reaches a minimum. Again, we can consider that in this case, systems with many subsystems, the minimum value of Q indicates upcoming fracture. And this was the case a few seconds later. The specimen fractured somewhere here. And this is also the case for bending of restored epistyles. I skip details. And you can see here the response of Q, of the entropic index. We start again from an increased value, and it decreases a little before the load causes fracture. It reaches a minimum, and then it starts increasing again. So we have too many indications that there are pre-failure indicators. I plotted here some of them as they are provided by the PSC, by the IB value, by the entropic index, and the natural time analysis. You can see here that in an area between 6 or 7 seconds and 30 seconds before fracture, we have indeed signs warning about some upcoming catastrophic events. Now, I will skip the discussions. I think the most important issue is that, yes, if we properly elaborate the data by traditional techniques like acoustic emissions or pressure stimulated currents, I mean using natural time or non-extensive statistical mechanics, we do obtain pre-failure indicators. The problem that could be discussed is it enough to prevent failures if you warn us 10 or 20 seconds before fracture? Yes, the answer is no. It is not enough. But this is the case for all existing methods of analysis of this data. So we hope that if we increase the sensitivity of the sensing tools, and if we combine the methods we use, natural time analysis, non-extensive statistical mechanics, perhaps we could draw conclusions even earlier, and then we could prevent catastrophic events. And as Filippo mentioned yesterday, I think this is a conference we cannot sleep. Yesterday night, while, okay, checking my presentation, I found a paper that it is not yet published. It is in press. And they gave an answer to us. They use a different technique based also on electric currents and electric emissions, but they measure the electric voltage, the electric potential. They analyze the electric potential exactly as I mentioned by means of non-extensive statistical mechanics, and they arrive to the conclusion that a few seconds before fracture, indeed, we have indicators. So this is encouraging, although I have not studied in detail the paper, which means that research all over the world is moving in this direction to use these alternative techniques and these improved sensing tools to prevent fracture and predict and prevent catastrophic fractures. I think we could stop here, Mr. President.
Yes, indeed.
Thank you very much.